Hi Science 30s, this is Unit D Energy Lesson 2. So in the notes package it says Harvesting Chemical Energy up at the top there. So continuing on kind of what we talked about from last lesson. So we know global energy demand is increasing due to various reasons. So what we want to look at is how is that energy extracted? How much energy are different compounds containing? So releasing, oh, I guess I need to full screen this. Releasing the stored energy in those petroleum products. So whether it's gasoline or coal or methane, any of those petroleum products, even if you think about wood, what it does is it actually requires or involves combustion. So that's one of the reaction types that we would have talked about in Science 10. So a hydrocarbon combustion requires oxygen as one of the reactants and produces both carbon dioxide and water vapor. So it also would require a hydrocarbon, but requires oxygen as a product or as a reactant as well, and produces the two products, carbon dioxide and water. So energy that's released from a combustion reaction can take many forms. So we can have radiant energy in the form of infrared and visible light photons emitted from the flame. Again, we didn't talk about infrared and visible light. That's something that's in Unit C, but radiant energy is important. An increase in the kinetic energy. So kinetic energy being the energy of motion, resulting in an increase in the collisions of the reactant molecules. And so again, that's the transfer of energy, or the ability to transfer energy. Oh, and so as those molecules collide, heat transfer occurs. So a change in temperature accompanies every chemical reaction. So sometimes it's negligible, that you can barely notice it, and sometimes it's very, very significant. So the total amount of energy contained by a substance is called its heat energy content. Which we'll represent with delta H, so that's the change in heat, or what will also, you'll sometimes see written as enthalpy. So that's the amount of heat that is contained. You would have talked about this in Science 10 as well. So if energy is released in a reaction, so if energy is actually a product of a reaction, that's considered to be an exothermic reaction. If energy is absorbed, that's called an endothermic reaction. And so that has energy being one of the reactants that it's required for the reaction to move forward. So these two parts you'll see when we do the calculations, or delta H calculations. So there's two little graphs below there. I don't have it in here, but you have it in yours. So the first one on the left there says exothermic. And so your y-axis, your up and down axis, is the amount of energy. And then along your x-axis, that's just saying the reaction coordinate. So as the reaction moves forward. So it says SM on top of the first one. I assume that stands for starting molecules. You could also put the word reactants there instead. So the reactants have higher energy than the products. So if they're, sorry, if I kind of draw it up here, this might help me. So again, this is energy, reactants. It has SM there. products. So our reactants have more energy than the products. So that means that that energy needs to be released. So this is the energy is released, and that delta H is negative. And then the other one looks the opposite, that your starting molecules or your reactants have less energy than the products. So in order to get to those products, you needed to input energy. So we needed to input that energy in order to get to the products. And again, that means that your delta H is going to be positive. So we needed to input energy in order to get to the products. So changes in heat content in a reaction. So that's delta H with that little R there. So again, heat content or heat energy content of a reaction can be calculated using the standard heats of formation. And so this equation, I don't have a data booklet. Oh, yeah, I do. Sorry. So this, in your data booklets, hopefully you have yours nearby as well. It's on page 5 in the data booklet. So on page 5 in the data booklet, at the top it says standard heats of formation of selected compounds, and it says energy formula that's down at the bottom. And this kind of beefy looking out of control formula is at the very bottom, and that's really the only one that we're going to use right now. And it looks like a bit of a mess, but it's actually not that bad once you get going. I shouldn't have done that box around it because now I can't really write. So to define the terms that we have there, so this is also something called Hess's law. Just when you're doing your Hess's law worksheet, it's using this equation. So delta RH, HR you can call it as well. So that's the, again, delta means change in. So that's the energy change of the reaction in kilojoules. So energy measured in joules. A kilojoule is 1,000 joules. This weird looking E actually means the sum of. So when we're talking sum, we're going to be talking about adding things up. And N is the amount in mole. You would have seen that in Science 10 and Science 20 if you took it. N is the number of moles of substance, represented by the coefficient from the balanced chemical equation. So you need to have your equation balanced correctly in order to do these problems. And overall is your standard heat of formation, or not overall, what you need is your standard heat of formation, which again comes from the data booklet on page 5. So to try to make that what looks kind of gross equation into words, it says the heat of reaction, so that's this part, so the heat of reaction equals the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. So that's what it's saying with all of these. So the sum of the heat of reaction, or sorry, the heat of formation of the products, subtract the sum of the heat of formation of the reactants. Don't worry, we'll do a couple practice problems for this one. So if the reaction is a combustion, then the heat of reaction will be equal to the heat of combustion. That's not super important right now. So we use the heats of formation that are given in the data booklet on page 5. I've already said that. a couple things. If you look at that big chart, the standard heats of formation, you'll notice that there is just not, you don't see anywhere like oxygen's heat of formation. That's because the heat of formation for elements is actually 0. Most heats of formation are actually negative. So if you look in that chart, most of them are negative. There's a couple positive, nitrogen monoxide, ethine and ethene, and benzene are all positive. I think those are the only ones. Most of the rest are negative. So make sure you pay attention to that negative symbol in the calculations. And sometimes the state is important. So you see that we have water, which is liquid or gas, so water vapor versus just water as liquid. So sometimes have a peak if you have more than one. So let's try to make some sense of this. This actually breaks it down into lots of steps, which is good. You might be like, oh, this is too many steps. I could do this in one whole big step. That's fine too, but sometimes it's nice to see all of your process because then we can see when or if you made a mistake. So this one already gives you the balanced chemical equation. So it balances with a 1 to 2 to 1 to 2. It's already balanced. Sometimes you'll have to balance it yourself. So using your law of conservation of mass. Again, these are our reactants. Reactants are what go into the equation. These are the products. That's what comes out of a reaction. So we have our reaction arrow in the middle. So it says use standard heats of formation to calculate the energy change for the combustion of methane. So CH4, that's methane, requires the presence of oxygen like we talked about and has the products carbon dioxide and water. So this is a combustion reaction. It's a hydrocarbon combustion specifically. Oh. Hydrocarbon combustion. So again, methane is the big thing in natural gas. What's being burned to heat your homes. So it says, look at the equation, find the heats of formation of each product. Multiply them by their coefficient and add them together. So our products, I need to write pretty small here. So our products are carbon dioxide and water. I'm going to put my balancing in as well there because it is important. Those coefficients are important for that N value. Remember that N we said is number of moles, so you get that from your balanced equation. I'm also going to just put the states because as we mentioned, that is important. So looking in the chart on page 5, we want to find our standard heat of formation for carbon dioxide. So carbon dioxide is CO2. We have gas. Our standard heat of formation is negative 393.5 kilojoules per mole. Sorry, it's hard for me to write small on this thing. And then the next one, so keeping our balance, because that's what we multiply each of them by. So this 1 comes from the 1 carbon dioxide. This is my standard heat of formation for carbon dioxide. This 2 comes from the balancing 2 moles of water. We have water as a gas. So we don't want to use the water as a liquid. We want to use water as a gas. So that's negative 241.8 kilojoules per mole. And so again, remember that fancy E, that's epsilon. That means the sum of, meaning I'm adding them up. So that's why I'm adding these two together. So the sum of those two together, again, those negatives matter. So the heat of our products here is negative 877.1 kilojoules per mole. Actually, let's just leave it as kilojoules per mole. Doesn't actually make sense in that case. So negative 877.1 kilojoules. So finding the heats of formation of each reactant. So our reactants, that's what goes into the equation. So our reactants are 1 CH4, 1 methane, and 2 oxygen. So O2 is oxygen when it's on its own is found diatomically as O2. So now looking at our standard heat of formation for each of those. So 1 times methane CH4 is negative 74.6 kilojoules per mole. And 2 oxygen. So if you look in your chart, you're trying to find oxygen. It's not in there because it's on its own. An element always has a heat of formation equal to 0. So plus 2 times 0 gets us negative 74.6 kilojoules. So now step 3 is subtract the reactants from the products. So products, subtract reactants. So the way that they decided which one to subtract from the other is looking back at this equation. So you see here, this says products, subtract reactants. So this was the sum of our heats of formation for the products. That was our step 1. This, the sum of the heats of formation of our reactants, was step 2. And now the step 3 is taking what this value was, subtract what this value was to get us our heat of reaction. So our delta H, our heat of reaction, is negative 877.1 kilojoules. Sorry, that doesn't look like an H at all. Now it looks like a backwards B. Subtract negative 74.6 kilojoules. I feel like I have a mistake in my notes here. I don't have a calculator. So negative 802 point, I think it must be 0.5. I had 0.3, but that's not right. So negative 802.5 kilojoules. So our heat of reaction for the combustion of methane is negative 802.5 kilojoules. So just sneaking back up our thing, it says if, how high do I go? So delta H is negative. So this is an exothermic reaction. And that should make sense, right? If we're burning methane in our house to heat our homes, we want to have energy being a product. We want energy produced, so that's an exothermic reaction. So now I'll give you a second, or you'll have to pause the video, I guess. Try this one. So this one again is balanced already, so you don't need to balance, but in the future you're going to need to. So try using those 3 steps, figuring out your heat of reaction for the combustion of glucose. So give it a try. Combustion of glucose, what is the heat of reaction in cellular respiration? So pause the video, try these 3 steps, and then I will go over it. So hopefully you've given it a chance, given it a try. So these are our products. These are our reactants. And again, this is balanced already. That's not necessarily always going to be the case. So So 6 CO2 plus 6 H2O. I think I'm writing way too fast. Our reactants is C6H12O6, so that's glucose. Sorry, it's impossible to read. Plus 6CO2. Oh, sorry. That should just be O2. 6O2. Good luck. So looking at our products, so 6 times carbon dioxide, again, carbon dioxide, we saw in the last one as well, so negative 393.5. Water, again, it's giving us water as, actually this time it's giving us water as a liquid instead of a gas. So instead of having water vapor as a product, we actually have water as a liquid. So make sure you use water as a liquid. So negative 285.8. So again, pay attention to those negatives. So 6 times negative 393 and 6 times negative 285, and we're adding those two together because again, the sum of means addition. So our heat of our products is negative 4,075.8 kilojoules. So our heat of our reactants, so we just have one, balances with a 1 for glucose, negative 1273.3. Plus 6. Again, oxygen's an element, so it has a standard heat of formation of 0. So this gives us and so to find our heat of reaction of the combustion of glucose, we take our products, subtract our reactants. I'm trying to write big so it doesn't look as messy. Negative 4075.8 kilojoules, subtract negative 1,273.3 kilojoules. Again, if you're subtracting a negative, you're actually adding. So that gets me negative 2802.5 kilojoules. I think I deleted this. You can do this practice problem, but I sent you actually a worksheet that I want you to do instead. So at the top of the worksheet, I believe it says, I don't know, heat of reaction. I think it's called the heat of reaction worksheet, or it might be called the Hess's Law worksheet. So one of those two. So what you can do, so I think on that worksheet, you need to balance, come on, click, click, click. Oh, it's being a pain. On that worksheet, I think you need to balance every second reaction. Oh my gosh, this thing's been a pain. You need to balance every second reaction. And then you can either do it as one single step. So using that big equation, you can do it as a single step, where basically you're putting step 1 and then step 2 after it. So subtract your step 2. And you can do it all as one step, or you can break it into those 3 steps the way I did. But again, on the worksheet, I think you need to figure out your heat of reaction. And then you also need to tell me whether it's exothermic or endothermic. So good luck with the worksheet. Send me an email if you need any help with any of it. And once you're done it, send it to me. Okay, bye.